So I welcome you to today's online facilitation. This is week 4 of our online facilitation of the course PHY 205. Today, we'll be looking at Module 2, Unit 3, Thermodynamics. Once again, I am Dr. Cyril Gwaza Afoy. As I said, the course is PHY 205. The course title is Introduction to Space Physics. This is our week 4. So let's introduce this unit. Thermodynamics is a field of physics that describes and correlates the physical properties of macroscopic systems of matter and energy. Matter, as we all know, is defined as anything that has weight and occupies space, while energy is defined as the ability or capacity of a physical system to perform work. Energy has the SI unit of joules. Hope you remember that energy and work are the same. Energy and work are the same. The principles of thermodynamics are of fundamental importance to all branches of science and engineering. The central concept of thermodynamics is that of the macroscopic system, defined as a geometrically isolable piece of matter in coexistence with an infinite, unperturbable environment. Okay. Now, the objectives of this unit 3 of Module 2 is 1. At the end of this unit, you should be able to, 1, define thermodynamics. What is thermodynamics? You should be able to define that. You should also be able to state the gas laws. You should be able to state the gas laws. No, the third objective is you should be able to derive the ideal gas equation. Derive the ideal gas equation. Then fourth, you should be able to differentiate between the ideal gas equation of state for a specific gas using mass m, small m, and specific gas constant r from the ideal gas equation. That's equation of state for any ideal gas using moles and the universal gas constant R star. Now you should also be able to show that the virtual temperature T subscript V is given by the equation shown there. You should be able to show that. Now, you should also be able to define geopotential. Be able to define geopotential. You also should be able to state the laws of thermodynamics. State the laws of thermodynamics. Then lastly, you should be able to explain adiabatic processes. Okay? You should be able to explain adiabatic processes. So let's make progress. Gas laws, equation of state, ideal gas laws, which is Boyce and Charles laws. So let's look at them one by one. For ideal gas equation, this equation is given by PV equals to MRT. PV equals to MRT is the ideal gas equation. That is equation of state for a specific gas using mass M, small m, and specific gas constant R. Okay. So whenever you see PV equals to MRT, M for mass, and so you should be able to know that PV equals to MRT is the ideal gas equation. Then PV equals to NR star T is the ideal gas equation for any ideal gas using moles and the universal gas constant R cross, R star. Then Boyle's law states that if only temperature, capital T in bracket, and mass, small m in bracket, are held at constant, volume is inversely proportional to pressure. Boyle's law states that if only temperature and mass are held constant, volume is inversely proportional to pressure. Okay? So what does that mean? Boyle's law is P1 V1 equals to P2 V2. That is at constant temperature and mass. Charles' law. Charles' law, we have two Charles' laws. The first one states that if only pressure P and mass M are held constant, the volume is proportional to temperature. The first Charles' law states that what? If only pressure P and mass M are held constant or kept constant, the volume is proportional to temperature. The second Charles' law states that if only volume V and mass M are kept constant, the pressure is proportional to the temperature. If only volume and mass are kept constant, the pressure is proportional to the temperature. All right, I hope we are making progress. Now, the virtual temperature and equations of state for dry and moist air is given by PD equals to rho R T. T means change in temperature, small change in temperature. Is the equation of state for dry air. Is the equation of state for dry air. Now, the virtual temperature T subscript V is a fictitious temperature allowing expression of the equation of state with moisture present using overall density rho, RD, and TV, given by rho, which is the overall density, equals to MD plus MV all over volume V. Okay. Now the overall density is the sum of dry air density component plus water component. And the virtual temperature, TV, is defined as the equation given there. As T subscript V is equivalent to capital T, which is the temperature, all over 1 bracket, square bracket, 1 minus exponential E over P into 1 minus epsilon naught, epsilon. Then in bracket, close the bracket, and then we have a square bracket, which is equals to T all over 1 minus 0.378 E over P, close bracket. Then P becomes the overall density and RdTd. Thus, the total pressure is given by gas law for dry air using the virtual temperature. Now, last equation, P equals to rho RdTv there gives the what? The total pressure by gas law for dry air using the virtual temperature. Note that since E over P is less than 1, and TV, that's the virtual temperature, is greater than or equals to T, as virtual temperature is greater than or equals to temperature. And rho, that's the overall density, is equals to P all over RdTv. Then moist air has lower density and is therefore lighter than dry air. Please take note of that. It's very, very important. Now, hydrostatic equation, geopotential, which is phi of Z, and height Z, and then hypsometric equation. Now we'll take them one by one, try to understand. For equilibrium static non-convecting conditions in which downward gravitational force is nearly balanced by pressure, the hydrostatic equation given rate of change of the pressure with density and local gravity G is given by del P over del Z equals to minus rho G into phi Z. Now, geopotential. Geopotential is defined as the work required to raise 1 kg to geometric height Z, and the unit of geopotential is joules per kilogram, and is given by phi of Z equals to integral from 0 to Z G into phi Z close bracket the Z. Thus, it is a function of height and the non-constant local gravity G. So I hope by now you should be able to define hydrostatic equation and write the equation, and also define geopotential and also write the equation. Okay. Now, geopotential height. Using globally average standard acceleration, GO, that's G subscript O, and geopotential is defined as Z equals to Z in bracket small z all over G naught. Note that the definition uses constant G naught as the local gravity, which is equivalent to 9.8 meter per second squared, defined exactly rather than varying G. Okay. Then the geopotential thickness of a layer between pressure levels is given by the difference between Z, Z1 and Z2, that is Z2 minus Z1, is equals to RD all over G naught, integral of P2 to P1, that's P1 to P2. The virtual temperature, TV, the P over P. Please note this equation. Geopotential thickness of the layer in pressure levels. Also take note of it. Now, hydrostatic equation. Hydrostatic equation using geopotential height Z and the local gravity G naught is given by del P over del Z equals to minus rho G naught. Or now, if you reverse this equation and take the reciprocal, you have del, you take the inverse, you have del Z over del P equals to minus 1 over rho G naught. Okay, that is for hydrostatic equation. Now, hypsometric equation, HE, is given by the geopotential thickness of a layer between two pressures using mean virtual temperature TV, is given by the difference between Z2, Z1 and Z2, that is Z2 minus Z1 equals to RD over G naught, and then the mean value of TV, that's the virtual temperature, ln P1, the natural log of P1 over P2. Okay, then the hypsometric equation is used for mapping pressure, that's pressure surfaces and layer thicknesses, which serves as a forecasting tool. I said this, it actually serves as a forecasting tool. Note that as the mean of the virtual temperature increases, the layer becomes thicker. And thickness of a layer is greater where air is warmer. What did I say? Thickness of a layer is greater where air is warmer. So let's look at the laws of thermodynamics. The first law of thermodynamics, this expresses the conservation of energy. Okay? The conservation of energy. The law of the conservation of energy. I hope you've not forgotten that. It says energy can neither be created nor destroyed, but can be converted from one form to another. For an ideal gas, working substance of mass m, fully enclosed in an insulated cylindrical container. When they say insulator, what does that mean? It means a substance that cannot conduct electricity, even heat, you know? So bounded at one end by a movable piston and at the other with a fixed wall. When heat dq, as change in heat, that is in joules, is added to the gas, the heat may increase. The heat may increase the internal energy of the gas, the U. The U is actually the internal energy of the gas, also measured in joules, and do work, dW, on or by the environment. In joules, in this case, interacting with the piston is given by the Q minus dW equals to du. The Q is changing what? In heat. dW is the work done, and then the U is the internal energy. These variables change independent of the manner in which the system moves between the two states. Specific heat, that is mass specific heat capacity of a gas at constant volume, is defined as C subscript V is equals to change in heat over change in temperature as a constant volume. Let me take that again. Specific heat of a gas at constant volume is defined as CV equals to change in heat over the change in temperature. And all this takes place at constant volume. Per unit mass, the units are therefore joules per kilogram, joules per Kelvin per kilogram. Okay. Then the first law is alternatively for alpha, which is equals to specific volume given by the Q equals to du as internal heat plus PdA. Now, the first law for thermodynamics for ideal gas expressed per unit mass is given by the Q is equals to CV dt plus PdA. All right. Now, the dry adiabatic processes and potential temperature. Adiabatic processes are processes for which the Q is equals to 0. No heat is added or removed from the system. When dry parcels of air are lifted rapidly so that there is no condensation or evaporation and no radiation, then the process is called what? Dry adiabatic. Please take note of that. Note that until condensation forms at the LCL moist unsaturated parcels that are lifted also follow a dry adiabatic, and for them the process is also dry adiabatic. For dry adiabatic, the condition is given by pressure multiplied by alpha, which gives us R dt. The dry adiabatic lapse rate in P coordinates is the T all over the P. Don't forget, alpha is what? Specific volume. Alpha is specific volume. By the T over the P equals to alpha over CP, C subscript P, and it's greater than 0. Okay. Now, self-assessment exercise. I expect you to do this. It says define your potential and write the mathematical expression defining all terms. Define your potential and write the mathematical expression defining all terms. Conclusion. In this unit, you are expected to have learned that PV is equals to MRT and is the word ideal gas equation, the equation of state. For a specific gas using mass and specific gas constant R, while PV equals to NR star T is the ideal gas equation. That's equation of state for any ideal gas using moles and the universal gas constant R star. R star stands for what? Universal gas constant. Also, that the adiabatic processes are processes for which change in heat is equals to 0. Q is equals to 0. No heat is added or removed. no heat is added or removed. That is for adiabatic processes. Summary. In this unit, we learned that Boyle's law states that if only temperature T and mass m are held constant, volume is inversely proportional to pressure. Volume is inversely proportional to pressure. And Charles' law 1 states that if only pressure P and mass m are held constant, the volume is proportional to temperature. The volume is proportional to temperature. Charles' law 2 states that if only volume V and mass m are held constant, the pressure is proportional to temperature. Please make sure you learn all these laws and the equations of state as they are written at different conditions. Okay, I say Charles' law 2 states that if only volume V and mass m are held constant, the pressure is proportional to the temperature. All right. So you can send questions to me through my email, or you can write your observations or questions on the course page, the Now portal. Okay, I expect you to do the self-assessment, which says what? You should define your potential and write the mathematical expression defining all the terms. You are expected to know the Boyle's law, Charles' law 1, and Charles' law 2. All this, I expect you to do this. Even the first law of thermodynamics, we are expected to know them and write the equations clearly. The first law gives what expresses the conservation of energy for an ideal gas of mass m, fully enclosed in an isolated cylindrical container, bounded at one end by a movable piston, at the other with a fixed wall. When heat, the Q, is added to the gas, the heat may increase the internal energy of the gas, the U, and do work and perform work on the environment or by the environment. So in this case, in J, that's in joules, this case interacting with the piston. And the Q, but that is the heat, minus dW is equal to the internal energy. Now we can make the work done, dW, to be the subject of the equation. So dW will now become the Q minus the U, that is the internal, the U minus, that is the internal energy. So wish you all the best. And I hope to see you next week, which is our week 5. Okay, as I said, send your questions to me through email or page on Now with time. So we shall and catch you next week. Thank you.